Yeah, let's continue from here itself. So I had stopped at extraction process I was explaining to you in the last class. Extraction of the metal from the concentrated ore. So I mentioned that there are two methods which you need to carry. One is you have to do the conversion of that particular metal into their oxide, whatever form they are. Okay, convert them into their oxide first, because oxide is easy for us, convenient it is for us to extract from that. To extract the metal is easy. Okay, so after that is over, still they have that oxygen present attached to the metal. So that oxygen has to be removed. So the last process what we are having is reduction. Removing the oxygen, it is called as reduction. So reduction of the oxide to the metal has to be done. So these two methods we just went through in detail. So in conversion of the oxide, first method we are applying is calcination. So calcination is heating the ore in the absence of air. Okay, so you are just trying to convert them, either if they are already in their oxide form, if there is water molecule or if there is any organic compound attached to it, if you oxidize them, okay, if you heat them, then those things will go out. See here, if water molecules are attached, water will escape out. You will be left only with the metal oxide, as you can see here in iron oxide case. So we are just having that iron oxide form. Then from there we are supposed to extract the metal. Then next here you see zinc carbonate. Zinc carbonate, you are supposed to heat it. So when you heat the carbonate, for carbonate it is easy, because carbonates are easily it will easily give out the carbon dioxide. So when you just heat them, it's enough for us to convert them into their metal oxide. Just heating will do. Okay, so you just heat them in the absence of air or very limited supply. But if you do that in the plenty of supply of oxygen, then it will again combine and give you this back. So I said it will be a waste of time, waste of the energy, if you are just doing it in the presence of oxygen. It has to be done in the absence. Okay, then after that, the next thing we have seen is roasting. Roasting is done for sulfide ore. So sulfide ore, you heat them. Sulfide ores usually is roasted. So roasting is the method where ore is heated. This ore is heated in the supply of air. Okay, so when you are heating them in the supply of air in a furnace at higher temperature, that will be under roasting. So sulfide ore, you can see here, sulfide ore with oxygen will give you zinc oxide. So it will form zinc oxide plus sulfur dioxide. Similarly, you can take another example also. One more example we can take. See, for example, lead sulfide if you take. So lead sulfide with oxygen will give you lead oxide first. It will form lead oxide plus the sulfur dioxide. Okay. So two examples are enough. It is enough for you to understand that sulfide ores initially when they are heated, it gets converted to oxide first. Complete reduction does not happen. Okay. So it gives you oxygen first, and then that oxygen has to be removed. So we'll move on with the next technique now, reduction. So reduction of that oxide now, in which form they are present. So from there you are supposed to convert them into their metal form. So now they will be in their metal oxide form. I'm generally writing now here, MO I am writing, irrespective of whatever valency they are having. Different metals will have different valency. Okay, so we can just write them as X and Y, but now let it be as MO. So they are in metal oxide form. So this metal oxide has to be reduced. Okay, so you need certain element which will take this oxygen and go. And finally, it will give you the metal in their original form. So for this, we make it to react with the carbon. Okay, coke is taken here. Coke, it is not that coke what you are thinking. This is carbon. Okay, it will look as if your charcoal is there. No, you have seen charcoal how it is. Okay, so similar to charcoal, but these are having better calorific value, means the temperature, it can heat at very high temperature. So that carbon, when reacted with this metal oxide, it will give you metal plus it will give you carbon monoxide. Okay, and this carbon monoxide also is a very good reducing agent. See, this also is a very good reducing agent. In some cases, what happens? Metal oxide with the carbon monoxide, it will react. This carbon monoxide formed also will help you for the reduction. Carbon monoxide will further combine with this oxygen and it will give you this metal plus carbon dioxide. Okay. So carbon can be taken. Now anything else can be taken. What do you think? Can we take something else as a reducing agent also? Yes, you can take, but you can take a highly reactive metal. Highly reactive metal will easily combine with oxygen and will reduce this compound. Okay, so it will reduce this and they will get oxidized. Okay, so highly reactive metals also can be taken as reducing agent. So that also I'll add. Plus you can use reactive metals. You can make use of reactive metals like aluminium you can take, zinc you can take. That could be also taken. Okay, I believe this till here it is understood, no students, what I said. In the extraction of the metal, we saw that there are two processes. I'll just go back once, I'll quickly revise. So when you are extracting the metal, finally when they are in their whichever form it is, after that concentrated form, whatever form they are, from there you should convert them into their oxide. From the oxide, you should finally convert them into their metal. Okay, so for that we are having processes here. So calcination is one method to convert into their oxide. It is applied for which kind of ore? You should remember it is applied for carbonate ore. It is applicable for carbonate and oxide ore. Some of the oxides ore, okay. But most of the time it is for carbonate. So carbonate will get converted to their metal oxides and carbon dioxide will escape out. And then roasting is another method. Roasting is done for sulfide ore. Roasting is heating that ore in the supply of oxygen. So when you supply oxygen, sulfur will go out as sulfur dioxide and metal will take that oxygen and for metal oxides. Example we have listed here. Then later on we are having the conversion. Now if they are in the metal oxide form, remove that oxygen. For that you need an agent who will take that oxygen and go. So your carbon can be taken. So they will be acting as reducing agents. Okay, these are the reducing agent who will take this oxygen and go out. Carbon monoxide formed also I said can be acting as a reducing agent that will further react with the metal oxide and give carbon dioxide. Okay, and reactive metals also could be used as a reducing agent. So now we will directly go for extraction process. I've taken first method. See, aluminium extractions are very important. You know, cheap and abundant. We are using so many aluminium metals in our daily life. So aluminium extraction, you are having their leaching process you have studied, which I said is for 3 marks. Now the first method which I am doing is for extraction of aluminium only by Hall-Herold's method. Okay, or Hall-Herold's process it is. Diagram is also important. You should study along with the diagram because diagram is also asked. Okay, in the exam for 3 marks you can expect. So along with the diagram you should study. See the setup how it is. If you see this diagrammatic setup, you can see it's a electrolytic method. Let me tell you, this extraction method is through electrolysis. So it is electrolytic method. You are going to supply electricity and then get the metal out of it. Extraction of metal is done through electrolysis. So whenever you do electrolysis, two electrodes we make use, no? One is cathode and the other one is anode. So you can see here anode they have taken is carbon rod. It's graphite rod, okay? Graphite itself is taken as the anode here, which is now here stuck to the copper clamp you can see. So they are anode and the lining you see here side, the lining of the tank, that is also made up of carbon, okay? So it is having carbon plus steel is also there here. Steel and carbon lining it is. So they will be acting as cathode. Okay, so that will be your cathode. What reaction takes place at cathode and what reaction takes place at anode? I hope you remember all that. Cathode is a place where which reaction takes place? Cathode is a place where reduction takes place, correct? Cathode is a place where reduction takes place. And anode is a place where oxidation takes place. An-ox and red cat. Okay, remember an-ox. Anode is a place where oxidation takes place and cathode is a place where reduction takes place. This is how I told you to remember red cat and an ox. So here oxidation and here reduction. Okay, so these places we have just mentioned here. Now see, you need an electrolyte, no? If you want that reduction and oxidation to happen, your solution should start moving, no, towards the respective electrode. You can't do that reaction in a solid state. You know, solid state, the movement of the ions does not take place. When you talk about electrolysis, okay, there will be ions which will be moving towards a respective electrode. So you need the solution. Okay, so here molten alumina along with the this Na3AlF6, it is Na3. I'll make it little darker here. I don't know if it is visible to you. It is molten alumina, Al2. It is Al2O3, molten alumina. And along with that, you can see another compound also is taken, Na3AlF6. This is cryolite. It is another ore of aluminium. You can see here, this is cryolite and this is our molten alumina. Okay, so this you are supposed to heat at very high temperature. It is in liquid state now. So when you heat them at very high temperature, you will get them in the liquid form, which will be acting as your electrolyte. These are your electrolytes. Okay, this is the electrolyte here. Okay, so there you can find now when they are maintained at very high temperature, you can find this aluminium in Al3 plus form and oxygen is O2 minus form. For us important is alumina here, so we will focus only on that. Why cryolite is added? Why not? You will have a question now. Why not like we can take only this? The problem is, okay, it is added so that you can like increase the conductivity. If you want to increase the conductivity, these things are added, okay? And it will help you to lower the melting point also. This is added to increase the conductivity. Okay, you want the reaction to happen faster. You want the movement of the ions to take place faster. So to increase the conductivity, this cryolite is added. And it even helps you to lower the melting point. It even helps to lower the melting point of the mixture. Okay, so that is the function of this cryolite. Now let's see how the reaction takes place. Before that, I have just displayed this picture. This is the industrial picture setup of Hall Herold's process. You can see here, these rods are there, no? Those are the graphite rods. It is placed at a higher level, and down you can see it is having this inside that it is outside is a steel covering. Okay, but inside you will see that they are having the graphite lining will be there. Here it is not visible, students. The inner picture we are not having, so just the outer covering you will be able to see here. And everything is clamped together with the copper ones. Okay, here it will be clamped together on this side. Now let's see the reaction wise what will happen here during the reaction process. Overall reaction, let me give you first. So on the whole, you are having alumina here. General equation I'm writing. Alumina is there in the solution, and then you have taken here carbon. Okay, so this will combine together. Aluminium will come out. This carbon will combine with the oxygen, and that will come out as carbon dioxide finally, and aluminium will be recovered. So aluminium you will get, and then you will get carbon dioxide. So if you balance this equation, 3 oxygen here, so it will be 2 on this side and 3 here. We are balancing the oxygen because it's odd number here, 3 and 2. So that I have multiplied, you will get 2 on the aluminium side and 3 on this side. Now you can balance the aluminium, 4 aluminium, so this will be 4. Carbon you can see 3, so this is 3. Okay, this is overall equation. Let me explain that at cathode and anode what is happening. See, this is how the setup is, I told you. Now, when you are having aluminium here, lot of Al3 plus will be there. It will be in the ion form. So, Al3 plus and O2 minus will be present. And anode is the place where we say oxidation takes place. Cathode is the place where reduction takes place. So, where this Al3 plus should start moving. Al3 plus is a cation, correct? So, cation should move towards the cathode. That's how you are supposed to remember. So, these cations which are there, it will be moving towards the cathode. So, cathode is where reduction is happening. So, this Al3 plus will take 3 electrons from the cathode, undergo reduction and form aluminium. Okay. So here itself I'm explaining that. Later I'll write that equation separately. Here itself I've told you. So in your solution you are having that aluminium in Al3 plus ion form and oxygen is there in O2 minus form. Okay, so that Al3 plus will start moving towards the cathode. Okay, so here cathode is the lining of your tank. The lining of the tank is the cathode part. Okay, so easily it will get attracted over there and start getting reduced. After the reduction is over, here it will be in the aluminium form. You can see a gray color liquid you are able to see here. These are the aluminium which are collected. So that aluminium will be taken out. Once they have collected it enough, then it will be removed out through this outlet. Okay, so aluminium is done there. So aluminium reaction is this. Okay, so at cathode you have to write this reaction takes place. Now come to the anode. Now this O2 minus is your anion. So O2 minus will start moving towards the anode because anode is positively charged, no? So negative ions will start moving towards that. And what do you have there? You are having carbon, no? This anode is made up of carbon. So this carbon will easily combine with the O2 minus first, undergo oxidation. Okay, so 2 electrons will be lost. That carbon will be losing it. Okay, carbon will lose those 2 electrons and oxygen will immediately combine with that, forming carbon monoxide plus 2 electrons. This is followed to you. These 2 electrons will be lost by the carbon. Those 2 electrons will be taken through the wire and it will come towards the cathode, correct? So then the reduction takes place. You have learned all this in electrochemistry. Hope you are able to recall it. So these 2 electrons which are moving over here will through the wire, it will come back to the cathode side. Okay, so this is one thing which can happen. But when more amount of oxygens are produced, more amount of oxygen can combine with the carbon. So I'll take now here 2 O2 minus. If 2 O2 minus combines together, then it will give rise to carbon dioxide plus 4 electrons will be lost. So these reactions you should know to write at the cathode and at the anode. Did you understand this reaction? What is happening and why it is happening over there? Understood, no? So slowly as the days, like as the reaction happens, as the reaction continues, you will see that your rods are there, no? That rod will become smaller and smaller because it is getting oxidized here. So carbon dioxide, since they are giving rise to carbon dioxide, as the reaction continues, your rod will get, no, it will vanish there because of formation of this gas. So it has to be replaced. If you want that reaction to continue again and aluminium has to be formed, immediately once the reaction is over and you see that the rod is becoming smaller and smaller, it has to be replaced again. Okay, so this is overall reaction. We will just write them separately. This was overall reaction here. Okay, on the whole, aluminium oxide combines with the carbon rod there, giving you aluminium and carbon dioxide. Now write them separately. It's better if you also write down along with me electrolytic reactions which are taking place at cathode and anode. This is how they will ask also. Electrolytic reaction at the cathode. We will write first at cathode. At cathode you are having the reaction happening. Then you are having at anode. Reactions are taking place at anode also. So cathode you have seen. Cations will move towards the cathode. And our cation is the aluminium. So aluminium is in, aluminium valence is 3 plus. So 3 plus aluminium requires 3 electrons. So you just take 3 electrons, what is required for the cation, and reduce them to the aluminium which will be in the solid state. Okay, finally, which will be collected. Then at the cathode what we had? Cathode we are having the carbon rod here. Carbon rod is combining with the oxygen which is there in the alumina. Because at higher temperature they are broken down into Al3 plus and O2 minus. Al3 plus went to the cathode side for reduction. At cathode, reduction is taking place. I am writing that also here. And anode is a place where oxidation is taking place. Okay, so oxidation where loss of electron happens. So who is going to lose here? The anode itself is going to lose. So carbon will be losing their 2 electrons. And oxygen coming over here will be in O2 minus. So both will combine and give you carbon monoxide. Those 2 lost electron will be 2 minus. Okay. Either this possibility is there, but when more number of oxygen combines, you know that it can give rise to carbon dioxide. So I am taking 2O2 minus. If more number of oxygen comes over there, then it will give you CO2. So 2 oxygen is combining. So that means carbon has to lose 4 electron. So 4 electrons over here. Understood, no students? It's easy. It is not difficult. You have learned all this. Cathode, anode, you know. Only thing you need to know that alumina, how they are getting reduced and oxidized at cathode and anode. Yeah, copy this down now. Copy this down. Okay, extraction of zinc. So I said from zinc carbonate, after calcination, we are getting zinc oxide plus carbon dioxide. So zinc oxide is treated with your reducing agent, which is coke here. This is the reducing agent. So if you want that coke to react with oxygen, just mixing will not do. You have to heat them at very higher temperature. So when you heat them at very high temperature, maybe around 1673 Kelvin, it will give you your metal plus carbon monoxide is formed. Second one is very important one. So you will have to listen properly, see properly, because there are different zones here. Different zones you will have to study here. So let me move on, because here it was only one equation. I believed you have finished writing it. We'll go for next one here. See, extraction of iron. Extraction of iron is done through hematite ore. I have shown the picture over here. This is hematite ore. Okay. Hematite ore. This one, this red color one you can see, no? These blocks are of the iron ore. And this iron ore is the further treated with the, you can see here these white cubes which I have taken, that is limestone. Okay, this is limestone. And below one you can see here, what do you think it might be here? This is the reducing agent what you are supposed to use. Okay, that's coke. This is the coke part. So I said it is having the feature similar to your coal. Coal and coke difference is only the calorific value. Otherwise, look wise, almost it looks the same only. Calorific value is different. So coke is used over here, and it will act as a reducing agent also, because iron has oxygen associated with that. So coke will be acting as a reducing agent here. This will be acting as a reducing agent as well. Now, what is the function of limestone? Why limestone is added? Limestone is acting as flux. Okay, I have told you what is flux. What is the function of flux here? Why flux is added? Flux combines with the impurities, that is gangue impurities, to form slag. Okay, so this flux, this limestone which is there, that will combine with the gangue. It will be combining with the gangue to form a slag. Okay, that you will see there later. Okay, so limestone is used there, acting as a flux. Just make a note of all this. What are we taking here and what are their function? Limestone is taken, I said limestone is acting as a flux. So limestone will combine with your gangue particles, that is silicates which are present, and give rise to slag. And then coke is acting as a reducing agent. Coke will act as a reducing agent. The ore taken over here is a hematite ore. The ore taken here is hematite ore, because that is available, abundantly available, so we make use of that. Now all of these in their powdered form, shall I move on? All of these in their powdered form are fed into a blast furnace. Okay, we make use of that furnace where the heating is done at very high temperature. The temperature, see, it is not around 1 or 2, it will be in like around thousands. It will be in thousands Kelvin. You are supposed to heat them. Very high temperature it will be. Okay, so at very high temperature it will be heated in this furnace. You can see it is long as your building is there, no, around 3-story 4-story building or more, like bigger than that it will be. You can see the length by seeing, looking at it only, you will understand how long it is. Okay, and from this side they start. Okay, from this side the Blast furnace, yeah, you have to learn about blast furnace. Diagram, not this one. I'll give you that brief, the smaller one. Diagram they have not asked, but can't say, okay, it's better if you learn. Zones at least you should know. What are the different zones where the reaction takes place? I'll give you that diagram also. So this is how it is. Okay, from up they have been fed. From this side the ore plus the limestone, and I told you the reducing agent, that is the coke. Everything will be added from this side, okay? And it will be heated at very high temperature. And down, from down region, this slag, see here, it is not correctly visible where it is, but then I have taken this schematic diagram. You can see here. This is a schematic diagram which you will be having to study, okay? Just see, it's easy to remember. It's not difficult. Just draw the funnel kind one, and then the furnace. Down you are supposed to mention. One is for the slag to be collected. This is for the slag. Opening is for the slag. And this side we are having opening for the iron. The iron metal which will be formed here, that will be collected from the another side. Slag will be collected from this side. And from here we are having the air. Blast of air means the hot air which is heated at very high temperatures pass through this. Okay, that's for the reaction. If you want that reaction to proceed, we have to pass, no, it has to be maintained, no, at very high temperature. So hot air is being passed from this direction. So initially that down region which is there, that down region will be at a very high temperature. The down zone is there, no? This zone will be at very high temperature. That temperature I'll just mention to you. This zone is this zone is where the slag formation happens. So it is zone of slag formation, this region. The down region is there, no? Zone of slag formation. The temperature is around 1073 Kelvin. This you will have to remember, students. You will have to remember the temperature also. For this, you have certain steps and some reactions are there. So you will have to keep that in mind. So 1073 Kelvin to 1273 Kelvin is the temperature zone. Okay, roughly this is the temperature. So that is zone of slag formation. Above this, the temperature will be little less because hot air is from the bottom region it is coming. So as it is going up, you can see that the intensity will reduce, no? So here the temperature will be little less. So this zone is for zone of combustion. This zone will be the zone of combustion in between one. So that temperature is from around 1773 to 1873. 1773 to 1873 Kelvin. This is the temperature. And above that, the lowest temperature, zone of reduction, where the reduction reaction takes place, is over here, zone of reduction. And that is 673 Kelvin to 973 Kelvin. These are the three zones. Three zones, three temperatures I have mentioned, and here is where the reaction takes place. So let's understand how that reaction is. Okay, I'll talk about the first one. Before going to the reduction, I'm talking about zone of combustion because this is the important region through which the reaction proceeds. The reaction begins from here. Okay, so the coke what you are adding, the coke what you have added is in the carbon form. And from this side, continuously you are passing that hot air, which are maintained at very high temperature. So your carbon which is coming out from the top will start reacting with this oxygen. Okay, so when they react with this oxygen, what they will form is initially carbon dioxide will be formed. Okay, so first thing what happens is formation of carbon dioxide. So this carbon dioxide, when they start going up, okay, when they are moving up over here, that carbon dioxide, because from the upper region continuously you'll be feeding that, no, the ore, limestone and coke will be continuously fed from that top. So that will react with the coke again and form carbon monoxide. Okay. So this things happens at the zone of combustion. At this temperature range, this reaction is taking place. Okay. So first thing you write down, I want you all to write down like that only. So write down first, you write about zone of combustion. Zone of combustion. I'm giving you according to the reaction. I'm not going according to the temperature here. So in zone of combustion, I said the coke which is there, that combines with the oxygen and gives you carbon dioxide. This carbon dioxide will move up, it goes up and it reacts with the remaining coke. I'll just write that this carbon dioxide goes up, it goes up and it reacts with the remaining coke. It reacts with the remaining coke to form carbon monoxide. So coke plus carbon dioxide forms carbon monoxide. Next is the further reaction. Okay, next is the second zone. This I am labeling as first now. The second thing what happens is in the zone of reduction will take place. Okay, in zone of reduction, this reaction will happen. So you have your iron ore there, that is Fe2O3. It is in Fe2O3 form. So that Fe2O3 combines with this carbon monoxide. Okay, it combines with this carbon monoxide and see what is being formed here. What is formed is, it will give you a mixture. Some amount, see, complete reduction will not happen. It happens in step. It will take place in step. So Fe2O3, can you tell me what is the oxidation state here? What is the oxidation state of iron here? Only then you will understand what is happening. In Fe2O3, iron is in which oxidation state? +3 state, correct? And +3 state to +2 state, the reduction will happen. Reduction means what? Gain of electron. So here this Fe3 plus will take an electron and get back. These are the two oxidation state, no, in which iron are stable. So it will give you FeO. Okay, first that will be formed. Complete reduction will not happen. It happens in step. Okay, so what will be formed is you will have FeO. Along with that FeO, some amount of Fe2O3 is still there. Okay, so that you have to combine and write. And when we combine this FeO and Fe2O3, I can write this as Fe3O4. Correct? Huh? This can be written like this, no students. You know that Fe3O4 does not exist. Okay, Fe3O4 is not a compound. It is a combination of FeO and Fe2O3. Okay, so Fe3O4 is formed with the carbon dioxide. Okay, so some amount of reduction has taken place here. This again further reacts. Okay, further the reaction will continue. So I am taking that Fe3O4 only because it's a combination of two oxides now. So Fe3O4 further reacts with this carbon monoxide where complete. Now like slowly the reaction continues. So FeO is formed plus carbon dioxide is obtained. Further if FeO reacts with carbon monoxide, then it will finally give you the iron and carbon dioxide. Okay, so go in step. First step, little amount of iron oxide is oxidized to FeO. So you will have a combination of both Fe3O4. So that Fe3O4 will further react with carbon monoxide, giving you FeO. Okay, now that FeO will further react with your reducing agent carbon monoxide, giving you Fe plus CO. Okay, is this understood? This zone of reduction is understood to you? You have to balance this, yes. You will have to balance this equation. So 3 we are having here, this side. This 3 is here, so multiply this by 3. This is 3 here, it has to be 2. So now it will be proper. 9 here. Yes, correct. The next reaction here 3 it will be. Yes, here it will be 3 because 3 iron we are having. So this will be 3 here. 3 FeO. 4 and 5 oxygen. You can see here 3 plus 2. 5 oxygen. Correct it is. And this is anyways balanced. The last one is anyways balanced. You don't have to balance. First two are also correct. It is balanced only. So it's not difficult. Now the last thing, see what happens. The last one, the third. In the third zone, where you are having that zone of, last one, zone of slag formation. Zone of slag formation. Since you are passing here limestone, which is calcium carbonate, CaCO3, and you are heating them at higher temperature. So it is obvious that carbonate has to break down, no? And that carbonate will break down to give you calcium oxide plus carbon dioxide. See, here also you are getting carbon dioxide. So, like from everywhere you are getting all of these gases, which can further react, with carbon, coke, and give carbon monoxide. So reduction reaction becomes easier when from so many places you are getting the reactant. So this happens first. Now this calcium oxide formed here is basic in nature, and the sand particles which are present there, the silicates which are present, they are acidic in nature. SiO2 it is. And it is non-metal oxide. Non-metal oxides are acidic in nature. Metal oxides are basic in nature. So both reacts with one another to form the salt. Okay. So calcium oxide combines with SiO2, silicon dioxide, to form calcium silicate, CaSiO3, which is your slag. So this is the third step. Okay, so where the slag is formed, and this slag I said is been removed out. You can see from this side. The molten slag will be lighter in weight. This will be lighter in weight, and that will come down. And metal ion, anyways, they are quite heavier. So metal will settle down, and this slag will be thrown out from this side. Okay, and these ions are collected from one side. Should I repeat this once again, or did you follow the equations? You were able to follow this, what is happening? Let me go back. Once I'll revise this. See, I told you in extraction of iron, we are taking hematite ore, which is Fe2O3. Your hematite ore is Fe2O3, which has been obtained after the calcination. After the calcination is over, you have seen there. Okay, the powdered form. After calcination, it is in Fe2O3 form. But along with that, there will be a certain amount of impurities. It is not in the pure form. It is just cleaned and brought. Okay, so it will have impurities present. That impurities should be removed. And both will look alike. That time you will not understand that the impurities, no, everything is in the form of stone there. So that impurities will be either silicates, okay, or any other compound which are present. Most of the time it is silicates. So to remove that silicate, we are adding the flux. The flux used over here is limestone, which is a CaCO3, calcium carbonate. Calcium carbonate itself is limestone. Okay, so limestone will combine with your impurities, which is also called as gangue, and it will give rise to slag formation. Along with that, you can see after the slag formation has happened, this Fe2O3 is there, no? From there, oxygen has to be removed. For that, you need a reagent. So, reducing reagent used over here is coke. So, coke is acting as reducing agent. Everything I said is fed together from the mouth of this blast furnace. From this side, it has been fed. Okay, and there are different zones where the reaction takes place. The bottom zone where the temperature is very high, because from this side you will be passing that hot air continuously, it will be passed from this side. Okay, so this region will be the hottest region, and you should see they are in molten state. See, iron is a hard metal. If metal is in that liquid state, you imagine how how dangerous also it will be. Okay, it's very very high temperature it is. Okay, if you stand far only, you can feel that heat. Because I remember this, why I'm saying that is because I've seen how that we were taken for the industrial visit. So I've seen how that blast furnace is, and when they get that metal in the no that yellow color, when they cut them, okay, how the cutting happens, and then how they are molded and all that. Okay, so it's that when you stand far only, you can feel that heat. It's very high. The temperature is very high over there. So that is the zone of slag formation. And above this, we are having zone of combustion, where the reaction takes place. The combustion reaction happens, where the burning takes place, no, where the carbon gets oxidized to carbon dioxide. That is your zone of combustion. That's in between. And above this, the zone of reduction. So zone of reduction is over here. That takes place at a lower temperature. Compared to all of these, they are at lower temperature. Oh, that is what we have written here. So in zone of combustion, I said the carbon reacts with oxygen, giving carbon dioxide. Further, this carbon dioxide reacts with the, okay, you are taking that carbon, no, coke is continuously passed. So when carbon reacts with that carbon dioxide, it forms carbon monoxide. which will be your reducing agent. This is your reducing agent now. After that coke has combined, now it is in carbon monoxide form. This reducing agent will combine with your iron oxide. Okay, and they will reduce that iron. So iron is in ferric oxide, it is in Fe3 plus state, which will get converted to Fe2 plus. So I said complete reduction is not happening. Step by step it is taking place. So first they will get converted. Few molecules will get converted to FeO. So you will still have Fe2O3 along with that. So you write them in Fe3O4 form. Okay, along with carbon dioxide. Now get them down, get the same thing down, make again the reaction with carbon monoxide, because further this reaction is continuing there in that blast furnace. So they come in FeO form now. This FeO further reacts. Okay, further when you are reacting, it will get back finally in the zero oxidation state. You see, finally it has got reduced because they are in metallic state now. So it will be zero there plus carbon dioxide. So we have got our iron, which will be settling down at the bottom of that blast furnace. And then the slag formation, where you have taken limestone to remove the silicates. So limestone, when you are heating in the blast furnace, it will decompose first. Decomposition reaction happens, giving you calcium oxide plus carbon dioxide. So that calcium oxide will react with your silicates, giving calcium silicate. Hope now at least I have made it clear.